In this lecture, we'll cover some basic laboratory math concepts or just some basic math concepts. And we will cover chapters 1 and 2. So we'll start off talking about basic arithmetic. In math, you have negative numbers and positive numbers. Negative numbers is any number that has a value that's less than 0. And that could actually be a decimal point value, but as long as it's a negative number on the negative side, then you can add those negative numbers. And the addition of negative numbers, the sum of two or more negative numbers will always be a negative number. So in this example here, if you were to owe someone $14 and also owe someone $45, then you would be in debt $59. Positive numbers is any number that has a value that is greater than 0. And of course you can add positive numbers. The sum of two positive numbers would equal a positive number. So if someone were to repay you $71 as well as $48, then you now have $119. Now let's take a look at addition of both a positive and a negative number. When you do this, the sum of an addition of both positive and negative numbers will be the sign of the larger number involved in the addition. So what you'll do is you'll look at in your equation for which number is positive and which one is negative. And then you would list typically your positive number first and then list the negative number. So in this particular example, if you have $37 in your bank account, but you have a bill in which you need to pay for $66, that's money that's going to come out of your bank account. So essentially, your equation would be written out 37 minus 66. So this negative sign here would kind of cancel out this positive sign because you are in debt. And so you only have $37 to cover your debt, which means you still owe $29. So you would be in the negative here. When subtracting two or more positive numbers, the difference is greater than 0, then that number will still remain a positive number. And so for this example, this you have $20 and you have a bill coming out of your account, so negative or subtract $5, and your answer will be 15. So from your $20, you pay someone $5, and so that leaves you with $15. And so this answer is a positive number because it has a value that is greater than 0. So this number is greater than 0. Now, if a positive number is subtracted from a smaller positive number, the difference will have a value less than 0 and will be a negative number. So in this situation, the larger of these positive numbers is being subtracted from the smaller. So you have $62 in your account, and then a bill comes out for $75, and guess what? You have overdrafted your account for a negative $13. The answer is negative. It's a negative number because 75 is greater than 62. So you have a negative 13. Subtraction of two or more negative numbers. When two negative numbers are subtracted from each other, the difference is negative if it is less than 0. So in this example here, let's just say your account is overdrawn negative $29, and then there's a transaction that came out from your account to Walmart, because we know we all get a lot of fraudulent Walmart charges on our debit cards. And so the bank catches that there was some fraudulent activity that overdue your account $29. And one of those fraudulent activities was for $14 at a Walmart. So the bank reimburses you. So this right here, this negative number, is where it's coming out of from the bank, where they're kind of rectifying the situation. And then that $14 is actually coming from the bank, going to go back into your account. So because negative 14 is subtracted from negative 29, these two double negatives here actually kind of cancel each other out. So instead of those being negative, it really should be a positive. So you can kind of see where those two have canceled out. That $14 goes back into your account, and guess what? Now you're only overdrawn $15, so a negative $15. The final answer is negative because negative 14 did not have enough pull to pull that final result into a positive number, or in other words, the bank didn't reimburse you enough money. And a couple more rules. If a larger number is subtracted from a smaller negative number, the difference will have a value greater than 0 and actually be a positive number. If a negative number is subtracted from a positive or negative number is actually added to the positive or negative number, then the two negatives become a positive. So that was that rule we discussed up top where the two negatives will actually become a positive. Subtraction of a positive number from a negative number. When a positive number is subtracted from a negative number, it is actually added to the negative number. So in this example, your account is overdrawn $14. You're still in the negative, and you got a transaction that comes out of $5. So let's just say this was another Walmart fund that come out. It's going to Walmart, not to you, or actually it's going to the frauds that are stealing your money. And so now your account is actually overdrawn $19. When a negative number is subtracted from a positive number, it is actually added to the positive number. And this is that two negative rule where you got two negatives turned into a positive. And let's just say in this example, you actually got $40 in your account today. And then you've got a transaction that comes out. And let's just say the bank noticed that that transaction was another fraudulent Walmart charge. And that $10 that had originally went to Walmart, the bank's reversing it. So that's coming out of that bank's account and it's actually going back to you. And then now you have $50 in your account. Multiplication or division of two or more positive numbers. When two or more positive numbers are multiplied or divided, the result will be a positive number. So in this example, 15 times 2, both are positive numbers, and so when you just do simple multiplication, your answer is 30, and that is the product of 15 times 2. 16 divided by 4, and then when you use the simple arithmetic to do this problem, your answer is 4. Multiplication or division of two or more negative numbers will result in a positive number. So a negative 5 times a negative 4 will give you a positive 20, or negative 45 divided by negative 9 will give you a positive 5. So the two negatives equal a positive rule again. Multiplication or division of negative and positive numbers. So the result with a mix of both positive and negative numbers with multiplication or division will give you a negative number. So that negative kind of takes over. And so in this example, negative 45 times positive 3, your answer is going to be a negative 135. So a kind of a scientific way you can kind of think about this, or to kind of keep this straight in your head. You would think about maybe you made a potluck potato salad to take to work, and maybe you use some spoiled mayonnaise. And so just one little bit of bacteria in that spoiled mayonnaise, in that entire potato salad, 1 or 2 organisms ingest it would be enough to make someone really sick. So that negative, even though that potato salad was great, tasted great, once that bacteria gets in the system, we're going to have a negative effect, and it's going to be an explosive negative effect. Next, we'll discuss the order of calculations. So when an equation contains numbers that are within parentheses, then the calculation should be performed on those numbers within that parentheses first. So here we have a couple examples where we will work out the parentheses first. So 43 times 2, that gives you the 86, and if you add that 86 to the 23, then you get your final product of 109. Here in the second example, 12 times 10, you would work this part out first. So 12 times 10 is 120, doing what's in the parentheses. Then the 120 added to the 31 gives you your final product of 151. Ratio and proportion. So this is something that gives students a lot of trouble. Students get this confused, especially when we start talking about dilutions. So a ratio represents the relationship of one value to another. So when we talk about a ratio, we talk about the relative amount of one component. So let's just say component A to component B. So we say a one-to-one ratio. So we talk about this here, it's A to B. When we talk about proportion, proportion is the relative amount of one component to the total amount of the substance or the solution. So with this, we talk about parts A in the total. So the total amount of the solution. And so we talk about a one-to-one ratio. It's one part A to one part B. And so this kind of represents that they're equal. And then with a 1-to-2 ratio, you have one part of A, but you have two parts of B. So you have twice as much of B as you do A. So let's think about this in terms of sweet tea. I'm from South Central Virginia, so depending on who makes the tea or where you go, it might be pretty sweet. So when I go to some restaurants, if I'm going to order a glass of iced tea, then I'll tell them to do it half and half. So I'll have them put in one part of their unsweet tea and one part of their sweet tea. So I have a 1-to-1 ratio, or half of that cup is sweet tea, half is unsweet. Now if I talk about a 1-to-2 ratio, then I might say, maybe I wanted a little sweeter today, or I know this restaurant's a little bit different, or my mom makes this tea a little bit different. So maybe I'll use one part unsweet tea and then 2 parts sweet tea. So that will make it just a little bit sweeter for me. And if we talk about the proportion, then what we mentioned up here, we have one part sweet tea and to the total of another part of sweet tea, so the total of the two would be 2. So that's a half ratio. Like I explained, half of that cup is sweet tea. In this here, if we have 2 parts sweet tea and 1 part unsweet tea, then we have 3 total parts. So the total would be 3, but only one of those is unsweet tea. So it would be a third of it would be unsweet, and then 2/3 of it would be sweet tea. Now, when we talk about ratios, proportions, we basically use this in the lab world when a new quantity of a substance is required that is on an existing ratio. And so we could calculate equivalent fractions, and this would be an example of using a ratio and proportions. So with a fraction of 2/4, it can be converted to something that's equivalent. And so here we have an example of 2/4, but we want to convert it to 8ths. So we can solve this equation by cross-multiplying the numerator, which is the top number, with the denominator, which is the bottom number of the opposite number. And so that's what they did here. They brought this 8 up, cross-multiplied with 2, the numerator, with the denominator. So you got the numerator cross-multiplied with the denominator. And this side, the numerator, which is x, cross-multiplied, brought up with times 4. And so when you work these out, 16 equals x times 4. And then, of course, you would take and try to get the x to the side by itself. So you're going to divide this on both sides. So divide by 4, that cancels that out. Divide by 4, which you see here, 16 divided by 4. And then that gives you an answer of 4. So therefore, 2/4 is equal to 4/8. Percents and percentages are used very often in the laboratory. So when we talk about a percent, that is the fraction with a constant denominator of 100. So that would be something like x over 100. And this is basically the quantity of a substance per 100 total parts. So that per 100 would be the total. So that's substance A in the total of 100. There are 3 different ways that we can actually write a percent, which means per 100. So the ways to write a percentage would include using the percentage sign. So in the lab, we use bleach, a 10% bleach solution, to do our decontamination of our countertops and things. So we would just write that out as 10% with a percent sign. But if we want to think about what is actually in that solution, that 10% bleach solution, then we would think of it in terms of ratio and proportion. And so a ratio, we understand that out of that total of 100 part proportion, that 10 parts of it is bleach, while 90 parts of it is the actual water, where we actually dilute it out with the water. And so that gives us our ratio. When we think about it in terms of proportion, then we think about that in the fractions. So we have 10 parts bleach to a total of 100 parts. So that is our fraction, which is our proportion. And it's also our dilution, because we did our dilution to actually make that 10% bleach solution. And so the fraction form is usually not written, but it is implied. We could also write it as a decimal. And so if we think about 10 cents out of 100, then that is our tenths, or 10 cents. So 10 out of 100 pennies. We know we've got 10 cents. And so you need to always remember that that denominator of 100 is kind of implied if you talk about a percentage. So it's something, a value out of 100. Now let's talk about rounded numbers. So when you're working in the laboratory, the preciseness of a measurement is determined by certain rules that guide the use of significant figures and rounding numbers. So rounding something off is a process of removing any sort of excess digits from a number so that it has the correct quantity of significant figures. Now we're going to talk a little bit more about significant figures in depth, but for now just understand that significant figures basically provide you with your confidence level of that value. And so when you're talking about your confidence level, you're just talking about looking for any sort of possible implied uncertainty of that number. So now let's talk about some of the rules for rounding numbers. So if the first digit to be dropped is less than 5, then the last remaining digit stays the same. So in our example here, you should round the number 13.563 from 5 significant figures to 4 significant figures. So we need to drop off that last digit, which is the 3. So because the digit to be dropped, which is number 3, is less than 5, then the remaining digits stay the same. So 3 is less than 5, we drop it, so everything else stays the same. If the first digit to be dropped is greater than 5, then the last remaining digits is rounded to the next highest number. So in our example here, 3.668 is 4 significant figures, and we need to round it to 3. And since our last number is 8, that means it's greater than 5. And that means that the last number, which is 6, needs to be rounded up. So we're going to round up our 6 to 7. And that gives us a number of 3.67. So we talked about if the first digit to be dropped was more than the number 5 or less than the number 5, but what if it is number 5? So if you're dropping number 5, what do you do? The last remaining digit is rounded to the next higher number if it is an odd number. So if it's an odd number, you round up. But if that number is an even number, then it's going to stay unchanged. So for this rule, remember that the last remaining digit is or becomes an even number. So you always end in an even number. And so with this example here, we've got 3.435, and we want to take that to 3 significant figures. So we need to drop that last 5. So we need 3 digits, from 4 digits to 3 digits, and dropping that 5. So because we get rid of that 5, the remaining digit is 3, which is an odd number. We need to make that an even number, so we're going to round that 3 up to 4, which gives us 3.44. So now let's talk a little bit more about significant figures and exactly what is a significant figure. And so we use these a lot in the laboratory to determine the precision of measurements. And so it kind of gives an implied uncertainty. And so when we look at significant figures, we're trying to figure out exactly how many numbers do we need, how many decimal places do we need to go out to make sure that we have some sort of indication of some sort of confidence in that number. So we're dealing with that implied uncertainty. With any measurement, there is an implied degree of uncertainty in precision of that particular measurement. So let's talk about the length of something. And it's measured to be 23.4 inches long when we use a ruler. And then when we look at that, we know that we're only precise to 1/10 of an inch because we only went out 1 decimal place. The actual measurement could be anywhere from 1/100th, give or take. It could be anywhere within that 1/2 of a tenth. The figure to go to the next 10th on that ruler mark. So we're somewhere in there. So there's still a little bit of degree of uncertainty because we know that it's right at 23.4, but we know that it could go slightly over, or could go slightly under that. Significant figures establish the degree of implied uncertainty of a measurement. So we know within the laboratory we can't report out 15 decimal places once the calculation is done for an analyte. We kind of got to trim that down a little bit. So we know that there's a little bit of degree of uncertainty in those numbers beyond what we established as a significant figure. So in general, the exactness of a group of measurements is dependent on the least exact measurement. So whichever one is not exact, if you've got some that go a few more decimal places in their measurement, then we know that that one that has less decimal places is least exact. So a scientific notation, we often use that in the laboratory world, using the scientific notation to indicate that those measurements are at a more precise level. And so we're going to talk about those scientific notations. But that kind of gives a simplified version of how to write a number if we need to take it out, let's say 10 decimal places. So rules with working with significant figures. If numbers that contain zeros within them, so it's within that number, then they are considered part of that number and therefore they are considered significant figures. The zeros are considered significant and they should never be dropped. So in this particular number here, these zeros are in the middle of this number, the 1001. And so there are 4 significant figures or 4 significant numbers within that particular number. And then this example here, The second one, we also have 4 significant figures. These zeros are in between both ones, even though it's after the decimal place. And so they're all 4 considered to be significant figures. Now, numbers that contain zeros at the end of the number, so here, this example, $520. If that number is greater than 1 and it contains zeros, the numbers at the right of that decimal place is considered significant. So in this particular example, this one would have 5 significant figures. So these 2 zeros that are to the right of the decimal place, because it is greater than 1, they're all significant. Now, if your number is less than 1 and it contains some zeros, and those zeros are to the right of that decimal point, then any zero that is in between the decimal point and that first non-zero number, so that first non-zero number is 7, and that would mean that this 0 here in the middle between the decimal point and the 7 is not significant. So this particular example only has 3 significant figures, 1, 2, 3. All right, so let's look at when to use significant figures in some various examples. So let's talk about addition and subtraction. For calculations involving addition and subtraction, the sum or the difference of a group of numbers cannot be any more precise than the least precise number in that group of numbers. So your least precise is going to be your one with the less decimal places, correct? So the final result of an addition or subtraction problem can have as many digits to the right of the decimal point as the least precise number involved in that problem. So in this particular example here, our first number, of course, has 3 significant figures, whereas our second number has 2 significant figures. But our second number here is the least precise because it has 2 significant figures. So once we do our math, we get 8.47. And so because we need to determine how many significant figures we're going to have, we use the least precise number of 2.2 with 2 significant figures. So we know that we need 2 significant figures, which means we've got to drop this number here. And then we go back and use our rounding rules because it's 7. It's higher than 5. That means we need to round this number here up. So we have 8.5. Multiplication and division works the same. The final result cannot contain more significant figures than the number within that calculation or in that equation that has the least number of significant figures. So when we work out this example here, and we see that we get 14.18 when we divide 6.27 by 1.5. And we know that 1.5 is our least precise number. It has 2 significant figures. And so we need to make sure that our value goes to 2 significant figures. So our value is 4.18. If we do 2 significant figures, that means we need to drop this 8. Our 8 is greater than 5, so that means we need to round up this digit here for a result of 4.2. All right, in this example here, when we multiply 4.978 by 3.34, we get a result of 16.62652. So that's a lot of numbers there. Well, when we look at this, we know that our number that is least precise would be this number here at the bottom. It has 3 significant figures, and this number here has 4. So we use our least precise, 3 significant figures. So we've got to get this number to 3 significant figures. 1, 2, 3, which means all of this stuff, these numbers here at the back get dropped. Our last number to be dropped is 2. It's less than 5, so that means that this will stay 16.6. Exponents and scientific notation. So exponents are a way to simplify complex multiplication problems. And so we do this by writing it with a number raised to a certain power. whereas x is the base and a is the exponent or the raised to or the power. And so the base is the number that is multiplied by itself. So your base number or your x number is multiplied by the exponent or the power. So in this example here, we've got 2 to the 4th power, or a base of 2 raised to 4. So that means that our base of 2 is going to be multiplied by itself 4 times. And so 2 times 2 will give you 4, and then 4 times 2 will give you 8, and then 8 times 2 will give you 16. Now with scientific notation, we kind of use this same concept of the exponent. And so with scientific notation, we use this to kind of simplify our calculations. And so the number is written, the number that you actually write has to be larger than 1 but less than 10. And so that means that you will use 10 as your number to multiply that number by. So for example, if we're trying to simplify our calculation, let's just say we ran our test and we got our result and our number came out to be this large number here. So what we want to do is kind of simplify that number, and we want to move this decimal place. Now the number of places that we move this decimal place. So this is all zeros here. Because it's zeros, we want to get rid of those zeros. Now they're still part of our number. We can't completely dismiss them because that is our value. We just need to make it a little bit simpler to use or simpler to view. So we want to move that decimal place until we get to a more manageable number. So 1, 2, 3, 4, 5, 6. And so if we were to move that 6 places to give us 2.53, then we know that we need to multiply that number by this large number here. 10 times itself 6 times, or 10 to the 6th power, whereas 10 is our base. And then that gives us this simplified number here. So this would be our total number. This is not another equation to work out. Now you could work this equation out and then you're just going to get this same number. But what we're looking for is simplified results when we're reporting. So this might be an example of a result that you would send out, and it would be 2.53 times 10 to the 6th. And this might be something else like milligrams per deciliter. So there's a little bit more to it. But this 2.53 would be your final number. And that's the mantissa number, which is actually, that just means that that is the number in which 10 is multiplied by itself in order to get that value. And that's what that means. So now we're going to talk about some of the rules when you are using exponents in scientific notations. So exponents used in scientific notations can be positive or negative. And so a negative exponent indicates that a number that particular number is less than 1. So let's use this example here, 0.0015. And so if we were to actually kind of put that into a scientific notation, we'd want to move that decimal place over till we can get a significant number and get rid of some of those zeros. And so we'd move it 1, 2, 3 places to give us 1.5 times 10, and we moved it 3 places, but guess what? We went to the negative side. So we're going to make that 1.5 times 10 to the negative 3. And so a negative sign is placed to the left of the exponent to indicate the negative exponent. If you were to have a positive exponent, or if it's moved to the positive side, if your number moves to the left instead of to the right, then we are not going to put any kind of indication that it is positive. So we would not put that it was plus 6. We would just indicate that it was 10 to the 6th power. It is assumed that if a negative sign is not present, then it is a positive number. If a mantissa number greater than 0 has an exponent raised to the 0 power, the exponent has a value of 1. So when we talk about 10 raised to a power when we're simplifying numbers, we talk about that power being 10 times itself. So this would be 10 times 10. And we know if we did 10 times 10, that would be 100. So if we were to do a 10 by itself one time, then that's just 10 times nothing. And so if you don't have anything to multiply it by, then that just leaves that value to equal 10. Well, 10 to 0 is a little confusing because if you're not multiplying 10 by itself and you're not multiplying it by anything, then what are you multiplying 10 by? Well, you're not. You are basically not using 10 in your number, so 10 is essentially 1 because you're not trying to multiply it out to a tens place. So if you were to run a result and you got 0.02, then if you wanted to simplify that, we moved that decimal places 2 places. We're moving it 2 tenths. That's tens. That's 100. So we've moved it 2 places, 10, or 2 times 10 to the second power. And what do we figure down here? 100. 2 decimal places is to the hundredths place. Tenths, hundredths. So if we were only to go 1 decimal place, 1 decimal place would move it 1 place, and that would be the same as 10 to the 1. Well, if we didn't move it any decimal places, then that would mean that, see, no decimal places. So we have 0.02 times 10 to the 0. So we didn't move that number any decimal places. So you can kind of think of this exponent here as how many places you move that decimal left or right. Our next rule when multiplying two mantissa numbers using scientific notation, the mantissa numbers themselves are multiplied by the exponents, but the exponents themselves are added. So you multiply the number but add the exponents. So in this example, you've got 10 to the a power, 10 to the d power. So you multiply your two numbers. So if this was 1 and that was 2, you'd multiply those two numbers. So 1 times 2 will give you 2 times 10 a plus b. Let's just say this was 2 and this was 2, so that would be times 10 to the 4th. When a mantissa number in scientific notation is multiplied by an exponent, then that mantissa number is multiplied by itself the number of times expressed in the exponent. And so the power of that exponent for that 10 number is multiplied by the exponent as well. And so this is written out as the mantissa, which is your number a, times 10 to the b exponent. And then if we raise that whole equation to the c exponent, then that means we need to multiply every number by that c exponent. So our example here is 2.5 times 10 to the second. And then that whole entire equation is also going to be multiplied by itself or raised to the second power. So we're going to multiply by itself. And there's a couple ways that we could do this. Our first way is just that we just kind of reduce that down. So we multiply both numbers, 2.5 squared times 10 squared, and that is also times 2. And if we were to work that out, we would get 6.25 times 10 to the 4th. 2 times 2 is 4. All right, so this number here, 2.5 times 10 to the second, if we were just to figure out what is that number not simplified, then we would move that decimal place 2 places. So that decimal place would go 1, two places. So that would give us 250. If we were to multiply 250 by itself, that would give us a number of 62500. And if we decided we want to figure out, reduce that number down, move that decimal place, we would go 1, 2, 3, 4 to give us 6.25 times 10 to the 4. Now we got to remember our significant figures. Well, our number in this particular equation was 2.5, two significant figures. So we need to make sure that we reduce this number to two significant figures. That means we drop this 5, but what was the rule on dropping a 5? So if you drop a 5, you need to make sure that the next remaining number, which is 2, is an even number, which it is. So that would give us 6.2 times 10 to the 4th. In division calculations involving the Matiza number in scientific notation, and so this would be our Matiza numbers here, a divided by c. Then the exponent in the denominator is subtracted from the exponent in the numerator of the equation. So first you have that equation. So here's our equation, our example of our equation of 7.95 times 10 to the 3rd divided by, so that's a divided by c, and divided by 2.5 times 10 to the 2nd. So that's our first number, a divided by c. We've got that written out here. 7.95 times 10 to the 3rd over 2.5 times 10 to the 2nd. So got to look at a couple of things. We got to divide a by c, but then we also have to subtract the denominator from the numerator exponent. So we got to look at the denominator is 10.2, so we got to subtract that 2 from that numerator 3, so that gives us times 10 of 3 minus 2. So when we work that equation out, that gives us 3.18 times 10 to the 1. Now we need to look at significant figures. Up top here we have significant figures. Our least significant figure is 2.5, so that means we've got to take this to 2. That means we're going to drop the 8. So when we drop the 8, that gives us 3 our next number means we have to round up to 3.2 times 10 to the 1. And then that gives us our answer to an equation with division. Now we can also do this problem a little bit different with division than what we just did. So instead of taking the denominator and subtracting it from the numerator of that exponent, you can do the opposite. You can subtract the numerator from the denominator, and by doing that, when you work out that equation, so instead of that number being on the top, we would bring 3 of those 10s down to the bottom. So we subtract them from the top, subtract them from the bottom. So 2 minus 3 will give us a negative 1. So our equation would work out to be 3.18 times 1 over 10 to the negative 1. And if you were to work that out, simplify that math, then you would get 10 to the 1. Now, if we wanted to use a calculator to figure out what this number really is, then what we would do is you could use a scientific calculator, or you could use a cell phone, and you're looking for the exponent key, or the one that says EE. Now, a lot of your cell phones, if you kind of flip them, or you have the option to do an expanded version of a calculator, but I know with an iPhone, if you flip it to the side, once you've got the calculator pulled up, you have an EE key. And so if you type in that number, 3.18 EE, your exponent, and our exponent in this particular number is 1. And so if we type in 1 and hit equals, it gives us 31.8. Well, the best way to perform an addition and subtraction problem is to first convert all of your numbers over that are in your calculation to some sort of non-scientific notation form. And then from there, you would do your problem, your addition or subtraction.
And so if we were to do that, if we were to convert 7.95 times 10 to the third to a non-scientific notation number, that gives us 7,950. We move that decimal over 3 places to the right. With 2.5, move it 2 places, that gives us 250. You know, if we work this out, it gives us 31.8, which should be the same number that you got on your calculator when you use your calculator to convert that Maltese number to a non-exponent form. Now for calculating log and anti-log, I'm not going to go over this in a lot of great detail because I have a lot of videos posted that I feel like can explain this way better than I'm able to explain it. But within the laboratory, the inverse of the exponential function is called a logarithmic function, and that is expressed as y equals a to the x power, or the x exponent. And the value of the logarithmic function is called the logarithm. In the laboratory, logarithms are expressed in a base of 10, so it will be 10 to some sort of power or an exponent, and that's called the logarithm, that exponent. So the logarithms can be either positive or negative. So if a value is between 0 and 1, so it's not 0 and it's not quite 1, that's a decimal place, that's going to be a negative logarithm. So your 10 is going to be raised to a negative power. With a positive number, that means that that number is greater than 1. So 10 is greater than 1, which means that would be 10 raised to the 1 power, so that's a positive number. The log of 1 is equal to 0, and we worked this out a little bit a while back, and that means that that logarithm is going to be 0. A logarithm is the inverse of the exponent, and logarithms can be determined by using the log, either a log table or using the log key on your calculator. And if you want to try that with these examples, you would just pull up your calculator and type in the number. So let's start with a 0.1 and hit the log key, and that gives you a -1. That would be your exponent. If you typed in 10, hit the log key, that would give you the exponent of 1. Type in 1, hit the log key, and that will give you an exponent of 0. The logarithm of a product of two numbers, or the multiplication of those two numbers, is the sum of the logarithms of those numbers. So in other words, you would get the logarithms of those two numbers and then you would add them. When performing a division calculation involving logarithms, the log of the denominator, or the bottom number, is subtracted from the log of the numerator. So you would figure those out and subtract those numbers. The logarithm of a number with a negative exponent is equal to the negative exponent multiplied by the log of the number. So you take that negative exponent and multiply that by whatever you get for the log of that number that that negative exponent was tied to. And of course, anti-logarithm or anti-log, and this is a number associated with a logarithm, and this is actually an inverse logarithm. And so this is determined by a calculator or using a logarithm table. If you were to use it on the calculator, you would enter that anti-log value, press the inverse function or the log function and the log function. And then with some calculators, it does require you to do like a shift key or anything to get that inverse function. The logarithm table, you would have to find the number that is given in a certain part of the table, and then of course you would go using the specific columns and rows and figure out what that number is, and then the combination of these numbers is the anti-log. So once you kind of go across and down, find where you need those point meets, that'll give you your value.